Welcome to support activity 15B, calculating and interpreting the chi-square test statistic. Imagine you are playing a dice gambling game. The dice has 6 sides. If you roll a 1 or 2, you win. If you roll a 3 or 4, you tie. If you roll a 5 or 6, you lose. So you play and you end up losing money. And you want to see if the dice was unfairly weighted toward the higher numbers. 1. Part A. You want to conduct a formal test to see whether a dice is unfairly weighted. Formulate 2 testable hypotheses for the scenario. So, hypothesis for this scenario is going to be that, as usual, there's 2 of them, the null and the alternative. The null we use h of 0, and always going to be against that what we need to do or what we need to test. So basically that h of 0, that's going to be saying that the dice is fair, that all outcomes are even. So basic h of 0, that going to be the distribution of dice result is even across all outcomes. However, that h of a, that's what we need to prove, or that's what we need to figure out if it's going to be really true or not. So the distribution of dice result is not even across all outcomes. However, we need to collect some data. And here the following tables show different possible results. And basic table A has 10 number of total rolls. B, C, and D has total number of 1,000, the number of rolls. So, do the result provide convincing evidence that the dice is weighted? So, if we try to go through the discussion here, is basic that I would like to just focus on that. This table has only the frequency, right? So you can see that if you get lower number, like if you roll the die and get 1 or 2, remember you win. But if you roll the die and you get a higher number like 5 or 6, you lose. So we're going to focus on the frequency for the lower number and the frequency for the higher number and try to compare. If I look at table B and table A, you will see that the frequency for the lower numbers is half of the frequency of the higher numbers. And that's obvious, is convincing that we are actually, there is something unfair here. So if we try to figure out is basic that which one is going to be more convincing out of B and A. So B comes first, or B is going to be more convincing since you have total number of rolls higher than one in table A. If I look at C and D, and you see that C has really the numbers of rolls is basic close to each other. And that's why C will be least convincing. But D still have basic a difference between the frequency for the lower number and the higher numbers. So since these tables A, B, and D are the one is basic as more convincing than C, so we should actually start with one of these. So B is the one actually have the most convincing as we agree. And if we try to choose between A and D, D will comes before, since basic D has more number of rolls. So B first, then D, A, and C the least convincing, since the result it comes as like as we expected. If the die is fair, this is actually how it looks, right? So basic, that's why that rank for us is gonna be B, then D, A, and C. So Question now is basic. If we go for number 2, let's calculate the chi-square test statistic using the counts in table A and B. So if I go for table A, and we find that observed count is 2, then 4 and 4. So then we're gonna actually calculate that expected count. Expected count, you get the probability of this category for this variable, and you multiply by the total number of rows, or basic that sample size. So the probability of getting 1 or 2, or basic the probability of winning is gonna be 1/3, and the probability of tie is 1/3. The probability of lose is 1/3. So every time I will multiply by the sample size. So 1/3 times 10, since the total rows here is 10, you get 3.33. Expected count, and you have observed count, you're gonna subtract it. So you're gonna get the observed minus expected and square the answer. So that difference is gonna be negative 1.33, and you're gonna square it, then divide that by expected. So this is how you calculate, or when you do chi-square test, you will get that observed minus expected square, and then you divide by expected. So you get that number, and you do the same for the rest. Then you add these numbers, and that's what we call chi-square for that table. It's gonna be 0.801. For the other table, you're gonna have different observed count, and also you're gonna have different expected counts. And expected count, the probability multiplied by n at this table is gonna be 1,000. So that's gonna be 333 is the expected count for this cell, and also for this and that. So basically you're gonna get the difference, which is subtract that observed minus expected. All the time observed minus expected. Then you square and divide by expected. So you get these numbers, count these numbers. That is basically gonna be the answer for, or basic the chi-square test. So look at your calculation, which table had a greater value for the chi-square test statistic, and why did it end up by being high? So the answer actually, basic obvious table B had a higher chi-square test statistic. And of course, it's clear also why we end up being higher, because I think that if you look at the square differences between observed and expected counts is gonna be large than the difference here. And that's why you end up by higher number. Part C, does a greater chi-square test statistic indicate more convincing or less convincing evidence of a weighted dice? Explain how you can tell using your calculation from part A. So a greater chi-square test statistic obviously will indicate more convincing evidence of weighted dice. This is because the test statistic quantifies the distance between what we observe and what we do expect from a fair dice. And the greater this distance, the greater the value of the statistic, and more evidence we have against the fair assumption. So as you see that the result at that out of table B is higher, because basically this means that the difference it was really large, and that's why chi-square test value get greater at table B. Part D, it is sometimes said the chi-square test statistic quantify how much our actual result defies our expectation. Explain how the calculation behind the statistic achieves this goal. The statistic does this by getting the differences between observed and expected counts in each category. Then we get rid of the negative and aggregate these differences by square them. Then we finally divide the square difference by the expected value to scale by our expectation and add them up. So we get scaled sum of the square distance between our observation and our expectations. Number 3, if we try actually to find that chi-square statistic value for all the tables, so that's my answer will be, which we have already did for A and B, and this is the one for C and D. So if we try to rank the tables from highest to lowest chi-square value, and if this order similar to the order you have in question number 1. So let's figure out the first part. If we try to rank these numbers so that B is the highest, then D second, then A third, then C the last one. So B, D, A, C. So actually, if we look at question 1, back to 1 is basic at the same rank, right? So this is basic that what we try to figure out if it's that the same or if that's similar to what happened at the beginning of this activity. So can you explain why it is similar or why it's different if you have a different one? For me, because similar is basic, I can say that the magnitude of the chi-squared value indicate how strong the evidence is against a fair dice. So the tables with the greatest chi-square value also show the strongest evidence against the belief the dice is fair. Part B. So let's do this for the chi-square statistic value from table D. So we're going to open chi-square distribution simulation using the applet, and we try to find the probability tab, and we're going to choose the degree of freedom. So we're going to follow that. So we're going to go to that applet and go to the chi-square. And then we go for find the probability tab and choose the degree of freedom. So according to our case, the degree of freedom is going to be 3 minus 1, which is going to be 2. And also we are using the upper tail. Then the chi-square test in table B was 2.28. And this the probability answer, the one we need is a chi-square distribution with degree of freedom of 2 is about 32%. So remember, I will go back and write my answer quick. So basically that 32% is the answer for this probability. So part C, would you say that table D provides convincing evidence that the dice is unfairly weighted? Why or why not? So you may have a different answer, but for this table, actually, the answer is going to be no, because basic that 32% of getting this result is basic is not really very high, and we cannot say there is a truly convincing evidence that the dice is not fair according to this table. So we're gonna stop here and end up that activity, and then I'll see you next time. Thank you.